Greetings, everyone. My name is Hot Tub. I am a learning assistant for Biz2A. This is my second quarter doing that, and I'm doing these video series because I found that a lot of students really just needed essentially extra class time with someone else teaching them besides the professor or your TAs. Nothing against them at all. Just, sometimes it's nice to have a third perspective, someone who has taken the class, kind of talk you through everything. Not to mention just it's extra time with the material. So I will be focusing in this kind of series on the major kind of topics of this class. I do need to give a disclaimer that all the professors kind of have different emphasis. Okay, some of them really target like plants and their biology, so the specific mechanisms of plants. My own professor really targeted protein, so we did a lot of pH, pKa, that sort of thing that other classes aren't doing. So rather than really try to hit everything and then you guys have to deal with what information do I need to know, what I don't, I'm going to hit just the parts of the class that are the big concepts that all professors are required to go over. And I might, add in little bits and pieces here and there of lecture-specific material and professor-specific material. This is not intended to be a substitute for discussion or lecture or reading the textbook or anything like that. It's just supplementary, okay? Just to try to help you guys out, give you more information, more strategies to learn the material. Okay, so the first kind of overarching topic we're going to talk about is chemistry. So it's going to be called Intro to Chemistry. Now, there are 6 major elements in our general biology. Excuse me, I'm a little sick, sorry. We have hydrogen, oxygen, sulfur, nitrogen, carbon, and phosphorus. They're each represented by H, O, S, N, C, and P on the periodic table, and then when we're writing them out, that's how we're going to show them, okay, because we don't want to have to write out their full names. Now, their valence electrons are very important. I have them written down, but you might want to go to a periodic table and understand how you know that hydrogen has 1 valence electron and nitrogen has 5. It has to do with the periods there, or sorry, not the periods, the columns they're in, the groups. Now that kind of breaks down in the transition metals. Luckily, we won't be going over the transition metals in this class. That is more for chemistry and very, very slightly in upper division biology. The only kind of special exception is phosphorus with how many bonds it can form, and that is because it can have an expanded octet, so you can't just use the octet and the duet rule. But in general, if we look at hydrogen will have a duet, meaning if we draw its Lewis dot structure, it'll have 1 and 2 electrons in that first orbital. Oxygen, on the other hand, if we draw that, if it were to be completely filled, so this is completely filled, oxygen would have 8, right? Because it's not in the second period. Hydrogen is, same with helium, but it is in the second period, so it's going to go back to it's going to use the standard octet. But now this would be if it's completely filled. If we were just writing out their valence electrons, we would have hydrogen, which is 1, oxygen, which would have 6. Let's do one more. Let's do carbon, would have 4. So that would be their basic Lewis structures. That's a good thing to get accustomed with, and you should go over that in discussion. But now, how do we know how many covalent bonds each will form? Well, however many it takes to fill the octet. So with carbon, we form 1, 2, 3, 4 bonds to fill its octet. Oxygen is 2, and hydrogen, it's only 1 because it has a duet. All right, so that's really all we need to know about the elements. Well, the specific elements, valence electron, and what bonds they're formed. The rest will all be building on this. So the first thing we're going to talk about is ionic bonds. This will encompass, probably I would say the most famous molecule known to, the general public, and that is sodium chloride. Whoops, I forgot to erase that. My bad. Okay. I was kind of writing my notes, myself notes, and I forgot to erase that. But so ionic bonding is, well, there's a way we can remember, okay? Ionic is the transfer of electrons, meaning that they won't be shared, they will just be given. So let's write out the structures of sodium and chlorine, because that is sodium chloride, right? NaCl, table salt, whatever you want to call it. Sodium has 1 valence electron. Chlorine has 7. If you are struggling with that, I would highly recommend, looking at the periodic table and seeing how I got 1 and 7. And like I said, it has to do with the groups they're in, the columns they're in. Sodium is in the first column of the main group, right? We're excluding the transition metals. Chlorine is in the 7th column. So sodium will be in the 1A column. Chlorine will be in the 7A. A represents main group. If you see B after it, that'll mean it's not in the main group. But anyways, what's going to happen, right? This is the transfer they're not sharing. So chlorine is very electronegative. We're going to get into what that term means in a second. It's going to steal the electron from sodium. So we can draw that in. And what we end up getting is a sodium without any valence electrons. It'll have 1 more proton than electron, so it'll have a positive charge. And chlorine will now have 8 valence electrons, and it will have 1 more electron than proton. So it'll be minus, right? To calculate charge, you always do protons, or number of protons minus number of neutrons. That's how we can calculate the charges. So now there's going to be an electrostatic interaction, right? We say like charges repel, unlike charges attract. One is positive, one here is negative. Those are opposite charges. They're going to attract one another, and they're going to create an ionic bond. And so how we typically draw it is like this. Whoops, I want a circle. And chlorine, this kind of has to do more with the chemistry side of it. Chlorine will be larger than sodium because it has now an extra electron that is repelling it. And sodium will be 1 less electron, so more pull. But that's way too chemistry for us in this class. That's something you'll go over at another point in time. But that's our general ionic bond, right? It's an electrostatic interaction. I can even write that. Electrostatic interaction. Okay. But what about the next type of bond? Covalent bonds. So these are all within a molecule. Ionic bonds and covalent bonds are all within a molecule. Okay. Covalent bonds is going to be still between 2 atoms within a molecule, but it's going to be sharing them, right? So instead of transferring, it's going to be sharing them. Covalent is the sharing of electrons. Okay, so How can we do this? Well, our carbon has 4 valence electrons. Our hydrogen has 1. This is a carbon-hydrogen bond. This is a very common covalent bond in biology. So what's going to happen? Well, we need to somehow satisfy the octet of each of these. Well, if we were to bring in, let's say, 4 hydrogens, okay, so 4 of them, we can rewrite this as, I'll even do them in different colors. We have carbon and its valence electrons, and then the hydrogens with their valence electrons. And now, as we can see, these two will form a bond. These two form a bond, these two form a bond, these two form a bond. And if we count, right, each bond, so one bond equals 2 electrons. Here are 2 electrons. Here are 2 electrons, 2 electrons, 2 electrons. This hydrogen here is surrounded by 2 electrons. This hydrogen here is surrounded by 2 electrons. This hydrogen here is surrounded by 2 electrons. And this hydrogen here is surrounded by 2 electrons. Remember, everything is being shared. Now, the carbon is surrounded by 8 electrons. So the carbon has its octet filled, hydrogen has its duet filled. Remember, hydrogen does not have an octet, it has a duet because it only has 1 energy level, and that energy level only holds 2 electrons. So they were each able to fill their octet, same with sodium and chloride. However, it's through the sharing of electrons, not the transfer of electrons. And also, if you're curious, this is methane, CH4. Okay. So now we need to talk about electronegativity. I kind of mentioned it earlier when talking about why chlorine stole the electron from sodium. But essentially, electronegativity is the tendency of an atom or a functional group. Functional groups are groups of atoms that act in a certain way to alter the function of a molecule to attract electrons toward itself. Typically, this is in a covalent bond. That's where electronegativity is really going to come into play, is how does this, is its impact on covalent bonds. So this is a periodic table, okay? Periodic table. As we go to the right, electronegativity increases. Now, as we go up the periodic table, remember, these are general trends. The transition metals kind of break this down, but we're only going to deal with main group. As we go up, electronegativity increases. So that results in the most electronegative element being fluorine. And you may be asking, well, why isn't it helium? Helium is the top right. Well, helium is a noble gas, right? If we drew its Lewis diagram, it already has a full duet. It doesn't need any more electrons. So we don't really consider it in electronegativity. Rather, it's all based around fluorine having the highest electronegativity value, and if you're curious, has a Pauling's electronegativity value of 4.0. Okay, this is a good trend to memorize, or at least understand why. Actually, I guess in order to understand why, you have to go deep into the chemistry, which we're not going to do. That's for another class. But at least memorize it, because that's going to be important. I'm going to really quickly turn down my... there we go. I saw my microphone is peaking, and I don't want that. Okay, so now I have a question. We have to rank these from least to most electronegative. And remember, these are all the elements that are important to us in biology. So we have C, H, N, O, P, and S. Well, if we look at our table here, Carbon has an electronegativity value of 2.5. Hydrogen has an electronegativity value 2.1. Nitrogen has a value of 3.0. Oxygen has a value of 3.5. Phosphorus has a value of 2.1. And sulfur has a value of 2.5. Okay, so we need to rank it from least to most, so we need to find the least one. Well, it looks like hydrogen and phosphorus are tied for least electronegative. Because hydrogen is the furthest to the left, I'm going to go ahead and say that one's first, although honestly, they're basically the same. So then we say phosphorus. Now we need to look at the next one. Well, it looks like it's between carbon and sulfur. I mean, once again, it can be up for debate. Once again, carbon is the furthest left, so I'm going to say carbon and then sulfur. And then our next looks to be nitrogen. And finally, oxygen. Once again, with the ones that are equal, you could probably flip them and be totally fine. I doubt you would be asked this. I very much doubt you would be asked about this on the test. I mean, it would be very obvious, like which one is more electronegative, oxygen or carbon. I mean, there's no debate there. So yeah, it kind of, yeah, I don't want to get into why, because I don't want to confuse you guys. That is for another class. If you took AP Chemistry, you would know this, but if you didn't, don't worry about it. So, electronegativity and the polarity of covalent bonds, right? I said electronegativity doesn't just affect ionic bonds, it affects covalent bonds. So you guys might have heard that, well, there's a polar nature to covalent bonds, right? A polymer is polar. Well, what does that mean? I gave us an example, oxygen bonded to hydrogen to kind of illustrate my point. But before we get into that, I want to give you guys an example, okay? So let's say you and I are friends, okay? We decide we don't want to have to spend the money both on 2 different notebooks for our classes. We're just going to share them. Maybe we don't have classes at the same time. So we're going to share one notebook. Well, if we were to just say, okay, 50-50, I get half the pages and you get half the pages. Everything's perfect, right? It's 50-50. Everything's equal. But what if I am taking a class that doesn't require notes? You know, it's really just a seminar. I'm listening in. There's nothing, and you're taking Biz 2A, where you're going to be taking a lot of notes. It doesn't make sense to split it 50-50, right? You're going to probably fill up your entire notebook, your entire half of the notebook, and mine is going to be untouched. So rather, it makes sense to give you more of the notebook and I use less. Maybe I only get 25% of the notebook and you get 75%. Well, then it's not 50-50, right? There is a different sort of nature to the notebook, right? There's almost a polarity. One side is more concentrated than the other. You know, you have more in the notebook than I do. So that's what's happening in a polar bond. Essentially, one side will have, if we look at a bond, okay, A is bonded to B, one side will have greater concentration of electrons than the other side. Essentially, the more electronegative side will have a stronger pull on those electrons in that covalent bond, and they will be more likely to be around the more electronegative element than the less electronegative element. And now how ionic bonds work is that pull is just so much, that difference is going to be so much that it's not going to matter what the less electronegative element does. It's really not going to have the electrons around it. So let's apply that to our oxygen-hydrogen bond. Oxygen has an electronegativity value of about 3.5. Hydrogen is 2.1. You'll see that this difference, 1.4, is a polar covalent bond, and we're gonna draw a dipole and delta charges to represent which side is going to experience more electrons around it. So our oxygen-hydrogen bond, oxygen is the more electronegative, so it's going to have more electrons, right? When you have more electrons than protons around something, it's a negative charge. So that means hydrogen will have less, meaning it's a positive charge. So it'll have, ooh, that is shaky. Yeah, that is not good looking. There we go. Okay, so I'll have that little plus sign, and the arrowhead will be going towards the negative side. And now we can represent that with a delta charge. It's a Greek D. Oxygen will be a delta negative. Hydrogen will be a delta positive. So that are how covalent bonds can be polar. Now, if there's not a significant difference in electronegativity, we say the bond is nonpolar. Okay. So now, I want you guys to pause the video here and go and fill in, fill in the difference between ionic and covalent bonds. And then in the second, I will write down all the things that I kind of have about their differences. Okay, that should have been enough time. If not, pause the, well, of course, pause the video if you haven't already. We're going to go through the answers. So ionic is the transfer of electrons. It uses full charges, and it results in electrostatic interactions through electrostatic forces, right? Positive and negative. There is a significant difference in electronegativity, right? And I can give you an example. Sodium chloride. Okay, if we look at covalent, covalent is the sharing of electrons. It has partial charges using the delta sign, partial charges or dipoles. It could also have no charges, which means it can be polar or nonpolar, depending on if it has charges. And this is dependent on the electronegativities, right? A greater difference in electronegativities, polar. Lesser difference in electronegativities, nonpolar. And I can give you guys two examples. Carbon bonded to hydrogen is a nonpolar. Oxygen bonded to hydrogen is a polar covalent bond. Alrighty. So, how to determine that? Well, we have this kind of little chart. Ooh, I don't know where this 1.8 came from. Alright, so between 0 and 0.4, this is a nonpolar covalent bond. Between 0.4 and 1.8, this is a polar covalent bond. So we'd that is not good, like that. This is covalent, and here we have ionic. So now there are some kind of weirdness in biology. The carbon hydrogen has a difference of 0.4, which is right on the cusp of nonpolar versus polar. But just memorize this in this class. the carbon-hydrogen bond is non-polar. Okay? In this class, the carbon-hydrogen bond is non-polar. Other than that, you can use this to determine if it's non-polar, polar, or ionic. Typically, you won't have to memorize these numbers because it's fairly obvious. You'll be able to understand which bonds are polar and which ones are not just by practice. You get used to it fairly quickly, in my opinion. Okay, so I have a question for you guys. I want you to identify all bonds and labels for two water molecules. So what you'll have to do is you'll have to draw them and label all the bonds between those two, or within two water molecules. Go ahead and pause the video. I'm going to go ahead and give you guys the answers, assuming you guys have paused the video and done this. So we're going to draw two water molecules. And I'm going to draw another one. You guys are probably wondering why I asked two. Why not one, right? There's a polar bond and a polar covalent, right? Two polar covalent bonds. Well, there's another bond, right? We need to talk about. This is a intermolecular bond, right? Between two molecules. And it is known as a hydrogen bond. So let's look at this water molecule up here, okay? That oxygen has, well, we know it's going to be a polar bond. So if we draw the dipole, it's going to look like that. We're going to have a delta positive charge here. But if we look below, that same thing is going to happen here. We're going to have a delta negative here. You see, delta negative, delta positive. They're still different charges. Even though they're partial charges, they still have some charge. It's just not a full charge. But they're still different partial charges. So there's going to be some attraction. So this positive negative, or sorry, delta negative and this delta positive will be attracted to one another, making use of this hydrogen to form this bond here, which we call a hydrogen bond. Hydrogen bonding is very important in biology. You'll see it appear over lots of things, including in proteins and amino acids. So, let's see. I want you guys to identify all the compounds with the dipoles. Here they are drawn. Once again, go ahead and pause it and do it yourself, and I'm going to go ahead and give the answers. Let's see. You guys probably wouldn't know this. I will go through an entire section actually later on in the slideshow about how to do bond line, but essentially each of these cusps here, each of these points, each of these ends represents a carbon. Okay, so really this is a carbon, 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 carbon. And you might be wondering, well, if those are carbons, that doesn't make sense because this carbon is only bonded to two other things. Well, great thing about bond line, we know what's there. It's an implied hydrogen. So we know there's two things bonded to it. It needs two other things. So this carbon here is also bonded to two hydrogens. It's just not drawn. It's implied through bond line. And I'll show you guys how to do this. But so really what you should be looking for is having electronegative elements, right? The only way we can get dipoles is to have electronegative elements bonded to not very electronegative elements. In this molecule here, it's just a bunch of carbons and hydrogens. So it wouldn't have a dipole, right? It's just carbon-carbon bonds and carbon-hydrogen bonds. So this guy, let me get rid, would not have anything, would not have any dipoles. This one, on the other hand, we have an oxygen binded to a carbon. That's a difference in electronegativity. We'll have a dipole. So this one, yes. Same thing here. Right? Oxygen binded to two carbons. each carbon oxygen bond has a dipole. They are not going in opposite directions. So when dipoles go in opposite directions, they cancel each other out and will result in an overall molecular dipole of nothing. But we're not talking about molecular dipoles. We're just saying, are there dipoles in these? And yes, there are, right? Carbon, oxygen is a dipole. Here, on this side of the molecule, it's a benzene ring with just carbon and hydrogen. So that won't have any. But here we have a nitrogen bonded to a carbon and hydrogens. That will have dipoles. How many? Well, it'll have 1. It'll have 2. But nitrogen carbon is also a significant difference. If we look at the table, nitrogen is 3, carbon is 2.5. That's a difference of 0.5, which is fully in the polar area, right? It's not right on the cusp, such as 0.4, which is the carbon-hydrogen bond. So that means we're going to have a third one here. So that one definitely has one. And then finally, we have carbon, carbon, carbon. The middle carbon, right, that is an isopropyl group. You don't have to know this until you get into organic chemistry. We have a dipole here, and we have a dipole here. So the latter 4 have dipoles, the first one doesn't. So now I want to convert between our standard form, which we call Kekuli, and bond line form. Okay? These were all in bond line. And it's a lot easier to draw in bond line than it is Kekuli, okay? Just to write out this molecule took so long. To write out this molecule, so quick because it's in bond line. So I want to take you guys through how to draw bond line, okay? How you do it, every end or point or cusp is a carbon. So if we draw a line here, that represents 2 carbons, right? We have an end and an end. If we draw another line, that now represents 3 carbons. We have 2 ends and a point or a cusp. And now we need 1, 2, 3, 4 carbons. So we'll just add one more line. Now we have 1, 2, 3, 4. And let's make sure if we draw in our implied hydrogens, this carbon here is attached to one other carbon right there. So that means it needs 4 bonds. It's bonded to one thing. It needs 3 hydrogens. 1, 2, 3 hydrogens. The carbon right next to it is bonded to 1 carbon. It's also bonded to a second carbon. 4 bonds minus 2 bonds existing, which means it just needs 2 hydrogen. The next one is the same thing. And then finally, excuse me, we have the the 4th carbon also bonded to 3 hydrogens. And you'll see that matches our molecule perfectly. So I'm going to go ahead and get rid of those hydrogens because we don't want to draw those in bond line. So our molecule would look like that. Okay. So now we have a bond line structure and we need to convert it back to Kekuli. Remember, each one of these points is a carbon. So we have a carbon, 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 and a carbon. So we'll say we have a carbon. Whoops. Bonded to a carbon. Bonded to a carbon. Bonded to a carbon. Yeah, come on. Stop doing that. Carbon. Carbon. Back to the original one. We have a hexane ring. Now this carbon here is bonded to a hydroxyl group. So an oxygen bonded to a hydrogen. There we go. That's our Kekuli structure. I'm going to move this up here. Finally, this is an aldehyde. I gave you a little note. An R just represents anything. It's not what we're focusing on, part of the molecule. The other way you could draw it is instead of having the R, you just draw a little line right there. It means it's connected to something, we just don't know what, and frankly, we don't care. So now we need to draw this in bond line. Well, we have our R group bonded to a carbon, which is just an N. That carbon is not binded to another carbon, so we just leave it there. And then an oxygen group, or our carbonyl. Okay, carbon double bonded to an oxygen is a carbonyl. So we should be done, right? Well, I'm sorry. I kind of threw this as a trick question because that hydrogen is actually significant. Okay, it's part of the aldehyde functional group, and so we do have to draw. It's not just implied. Whereas if we look at the hydrogens in the first one, right, they were implied. They were not part of a functional group. And so we don't have to draw them. But I'm hoping you guys caught my mistake somewhere on this page. I intentionally left it because I wanted to make sure that you guys really understand bond line formula. Hopefully you guys were yelling at your screen that I was forgetting this. If you didn't, I would, really spend some time learning about bond line formula because it does make things a lot easier, and when you're identifying compounds, you'll often have to do it in bond line. And my mistake was each of these carbons here, they're carbons, right? They're implied, but also the hydrogens are implied. I did not draw hydrogens in. So this carbon here is only bonded to 2 carbons. It needs 4 bonds. So we need to draw in all the hydrogens. And now you'll see why bond line is so much faster. I don't have to draw in all these hydrogens. And we do have one more. It'll be right there. So that got really complicated, right? Drawing Kekuli structures is quite exhausting because you have to draw so many, especially if you're trying to draw lipids. Lipids are just really long chains of everything, so having to draw them is kind of painful. But now we've successfully converted between them, okay? Everything that is implied in bond line is left implied. Everything that is necessary, so that hydrogen in the aldehyde is necessary and is part of the functional group, so we must draw it. Excuse me. All right, hopefully that makes sense now. We'll move on. My goal is to not have this be a ridiculously long video, but you never know. All right, so in chemical compounds, what do the different letters represent? Well, they represent elements, right? Na, carbon, iron, I don't know, francium, uranium, gold, etc., right? They all represent different elements. And what do the solid lines between letters represent? These represent covalent bonds. And now what bonds are polar? Well, they are covalent bonds between atoms with significant difference in electronegativity. And this significant here, right, is kind of arbitrary, right? It needs to be somewhere between about 0.4 and 1.8 difference in the Pauling electronegativity scale. That'll be a polar bond. Anything more than that is likely to be ionic. There's also kind of, everything is more confusing when you get to upper division stuff where it's not really covalent ionic. It's more like They're mostly covalent and mostly ionic, but they'll have properties of both. But we don't need to get into that now. That is for chemistry. Just the standard covalent ionic terminology is sufficient for us. All right, so I have a question. Which of the following molecules can hydrogen bond with another molecule? To answer this, I gave you guys a little list of what you need. So the first thing is you need an H bonded to a very electronegative atom, so such as O, N, or F, oxygen, nitrogen, or fluorine. And then the second thing is this H is attracted to the delta negative or a full negative, right? So you can actually get attraction with a hydrogen bond with a ionic compound. That's how, what's it called? Ions dissolve in water is by that. And then the essentially negative charge of another element. So, can water form? Well, yes, we know it has delta negatives and delta positives. So, yes, it can. This amine, so NH2 bonded to R, that's an amine. We do actually have dipoles, right? So you have a delta positive H that will be able to H bond. Now, how about an aldehyde? Well, this one's kind of tricky. How is this hydrogen going to respond? That would be kind of crazy. In OChem, you'll learn if it does or if it doesn't. But for us, that would be kind of difficult. However, remember, to hydrogen bond, you can either be a donor, right, give away a hydrogen, or you can be an acceptor. This oxygen here has a delta negative charge. So it can accept a hydrogen bond. So yes. All right, it doesn't say can it donate a hydrogen bond. All we're saying, can it engage in hydrogen bonding? So it can either be a donor or an acceptor. Let's see if this carboxylic acid. Well, this hydrogen here will have a dipole. So it can donate. But this oxygen also has lone pairs. So it can accept right here. Same with this oxygen. So this one can, on multiple fronts, it can be both a donor and an acceptor. How about methane? Well, we said the carbon-hydrogen bonds are strictly nonpolar in this class. So unfortunately, it cannot hydrogen bond. It does not have a delta positive hydrogen that it can that can be attracted to a delta negative of another atom, even if that, other molecule. Even if that other molecule could H bond, it could not H bond with methane. So now I have a question. How many hydrogen bonds can one water molecule form? Well, if we draw them out, we have a hydrogen bonded to an oxygen, bonded to another hydrogen. Here we can have one donor. Here we can have a second bond be a donor, but it also has two lone pairs, which can each accept a hydrogen bond. So it can donate two hydrogen bonds, it can accept two hydrogen bonds. So that means 4 H bonds in total. Okay. So now let's talk about molecular dipoles. Essentially, if a molecule has a single dipole, it'll have an overall molecular dipole. If it has multiple, we need to look at the direction of them. Okay, if they're going in the exact same direction, then it doesn't matter. Actually, I think I drew this in the wrong way. Oopsies. If they're going in the same direction, they will cancel each other out. If they're going in opposite directions, they will cancel each other out. If they're going in the same direction, they will do what's called adding together to make an overall molecular dipole. So that's what you got to look for. Let's even consider for the moment that methane, the carbon-hydrogen bonds, are polar, right? We'd end up getting something that looks like, actually, it should be this way, right? See how this guy and this guy are going in the same exact direction? This guy and this guy, are in opposite directions. They're going to cancel each other out. So even if the carbon-hydrogen bond were polar, methane would still be non-polar because all the dipoles cancel each other out. So that's two ways you can make an argument that methane is non-polar. And I wouldn't say necessary symmetry. Actually, take this back. I would just say if you have dipoles, right? If all the dipoles have another dipole that cancels it out, there would be no molecular dipole. Okay, so how does polarity affect solubility? Well, let's see what happens if we put NH3 in water. NH3 looks like this. We end up getting dipoles going towards the N, a delta negative, and each of these hydrogens has a delta positive. When we surround this in water, what's going to happen is the delta positive is going to be attracted. The delta positive on the hydrogen is going to be attracted to the nitrogen. And the delta negative of the oxygens are going to be attracted to the delta positive of the hydrogens in the amine. So we'd get something that looks like this. How about sodium chloride? Well, what'll happen, right? We'll end up getting sodium plus Cl minus. Well, our water molecules are going to be looking like this. Oops. Hydrogen, hydrogen. I'm trying to go quickly. That's what we'd end up getting. Now let's say, what if we threw in methane in water, right? Well, the water molecule isn't going to like it, right? It's not going to be attracted because there are no charges, right? Or there's no partial charges. So what's going to happen is all the water molecules are going to be over here. All the methane molecules are going to be over here. If you've ever put oil in water, they separate from each other and you can see a distinct line. It's because of this. So hopefully that makes sense now. It's pretty cool. So I had spoken earlier about functional groups. Now I just want to go a little bit more in depth about them. In this class, we're going to talk about 6 main ones. We have the methyl group, the phosphate group, the carboxylic acid, the alcohol, the amide, and the amine. Okay? Methyls are nonpolar, right? It's just CH3. Phosphates are charged. Carboxylic acids are polar. You could also make an argument that the phosphates are polar, but it's better just to say charged. Alcohols are polar. Amides are polar. And finally, amines are also polar. Typically. This is, that's just looking at, right, what is there. We have polar things The dipoles are not going to be canceling each other out, so they make an overall um, molecule that has, oh, excuse me, a molecular dipole. Okay. Very quickly, though, I want to go over some notation. I briefly said R means anything. R prime just means it's anything, but it's different than R. Technically, you don't need to say that. You can just say R, R, R. But someone could come around and be like, well, technically, R is just one thing. So if you have three different things bonded to a carbon, you need to say it's R, R prime, and R double prime. You know, it's a technicality, but it's good to know that. So this just means there's a carbon bonded to a hydrogen and then three other things that we don't really care about. Okay, really quickly, I want you guys to classify this as polar or nonpolar. Well, methane we know is nonpolar. Here is an alcohol. Okay, we have this group attached to a carbon bonded to two hydrogens, and then our group will have a dipole. This will be polar. Okay, really quickly, I need to go over two special functional groups. So carboxylic acids, this guy here, can be deprotonated, meaning they can lose their hydrogen, right? Acids are hydrogen donors in water. Bases are hydrogen acceptors. So carboxylic acids can actually lose their hydrogen, becoming this guy. Amines are bases. They can become protonated, meaning they can take a hydrogen, resulting in this guy. So amines can be protonated, right? Bases can be protonated. Carboxylic acids, or acids in general, can be deprotonated. That will come into play, especially if your professor goes a lot over proteins and amino acids. You will have to understand this and how pH and pKa of a protein work together to alter it. Okay, we're going to end this, I think, with going over the macromolecules. There might be something else. I can't really remember. But we're going to talk about the macromolecules. The first one is the carbohydrate. Break it down really, it's carbo, meaning carbon, and hydrate, meaning water. So for every one carbon, well, for the carbons we're looking at to determine it's a carbohydrate, it'll have 2 H's and 1 O. In the overall structure, you'll have 1 carbon per 2 hydrogens per 1 O. So resulting in the formula CnH2ON. And now if we were to look at this is the bond line formula, or I guess not, this is actually, I guess technically this would be a Fischer production, but you don't need to know that. This is kind of the straight chain formula for glucose, which is C6H12O6. I want to highlight, look, this is a carbon, right? Oops. Hey, why'd you do that? There we go. This is a carbon here. This carbon is bonded to 1 H and 1 OH. H plus OH, there's your water. So it's kind of hidden, but if you look for it, you can find it. Here's 1 water, 2 waters, 3 waters, 4 water. It's perfect, right? So essentially, carbohydrate is you're gonna be able to find water in it. It'll just be kind of separated. Okay. Nucleic acids, on the other hand, you're gonna find it by having 3 parts: a phosphate, which is this guy. I'm gonna phosphate. The sugar, this guy. For DNA and RNA, it stands for deoxyribose, meaning it's a 5. It's a pentagon. Ribose mean 5. um, ribonucleic acid, and then RNA is ribonucleic acid. So deoxyribonucleic acid, ribonucleic acid. That will come into play later of why those are different, what that means. That'll be kind of the last few weeks of class. And then finally, we have our nitrogenous base, which is this guy here. There are multiple nitrogenous bases. This is one one. I honestly don't remember which one it is. You don't need to know your different nitrogenous bases for this class. In fact, if you need to identify them, you will be told them. You won't have to memorize them. Actually, unless your professor somehow just decides to make you do that, which I kind of doubt it, but you never know. But so that's how you identify nucleic acid. Phosphate bonded to a sugar, bonded to a nitrogenous base. Finally, we have lipids, okay? Lipids are generally nonpolar. However, they can have polar ends. Actually, in this molecule here, it does have a polar end, right? It has a carboxylic acid. But all of this over here, that's all nonpolar. And this is a kind of a organic chemistry thing. But once about you have 4 carbons in a chain, the molecule overall kind of becomes it has nonpolar tendencies. However, it will have some polar because of this guy. We don't need to get into that. In phospholipids, when we talk about cell membranes, this will come into play, but we will talk about it when we get to cell membranes. So, they're generally nonpolar. They can have nonpolar ends. The key here is they have lots of carbon and hydrogen. Remember, in bond line, each of these carbons is attached to a hydrogen, right? And so on and so on and so on. I don't want to draw those. It's a lot of carbon and hydrogen. And most of the time our lipids will be long chains. So if you see a long chain like this, it's most likely a lipid. However, it's not all of them, okay? This guy here is cholesterol. Cholesterol. I think that's how you spell it. I don't know. I don't really care, honestly. But see how it has rings. So we can't just use straight chain, okay, or chains, because there are some rings that are lipids. However, if you notice, let's zoom in, it's a bunch of carbon, hydrogen, and carbon-carbon bonds. Hydrogen. There's one OH group down here. That's not enough for us to say, oh yeah, that's a carbohydrate, you know. It's mostly carbon hydrogen, so we're going to say it's a lipid. Cholesterol is very important, and we'll get into that in cell membranes. Man, my throat is dying. But yeah, so that's how to identify lipids. Really, you have cholesterol. Just really look for a metric ton of carbon hydrogen. Proteins, I actually really like this diagram. It's all nice and colorful. Proteins are made up of amino acids, and that's how you're going to find, or that's how you're going to notice what proteins are. Really, you're going to be looking for the NCC repeating backbone. You could look for the functional groups. You can memorize all 24 functional groups, or maybe it's 21. I don't remember. You don't need to know it for this class unless you want to do that, in which case you would just search for the functional groups, and if you find all the functional group, or a bunch of them, it's a protein, but that's not fun. It's terrible. The rest of us, the normal people, not the tryhards, are going to search for this NCC repeating backbone. Okay? So, essentially what we have here is an amino acid is made up of a amine, an alpha carbon, and a carboxylic acid here. Okay? We'll get more into the structure of these when we talk about proteins, because this is going to be really, really important. And how we get long strings of these, essentially what's going to happen is you take 2 amino acids, this hydrogen and this OH will be lost, and then this C of the other molecule will bind to the N. You'll have, when you put these right back to back, the ends, that the C of the carboxylic acid will bind to the end, and when you combine H and OH, out pops out H2O. But we'll get into that when we talk about proteins. I just want you guys to understand the structure of amino acids because that's kind of the structure of proteins. Well, there's four. We'll get into that when we talk about proteins. That'll be an entire lesson in and of itself. But so the thing is, to identify a protein, look for NCC. You'll just see NCC, 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 dot, 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 going on forever and ever and ever. That's a protein. Okay. To tie it all together, functional groups, as they're in their name, right? Functional groups have a function. They impact macromolecules, right? They change the function of macromolecules. Okay. The best example I can give that will make sense to, or will really make an impact on you guys is that nitrogenous bases pair due to hydrogen bonding because of their functional groups. Okay. So here, how we get base pairing is that only adenine and thymine, in this case, adenine has, right, the first from the top, it's donating a hydrogen bond, and then it's accepting. Thymine, on the other hand, is accepting a hydrogen bond and then donating. Your four nitrogenous bases, adenine, thymine, guanine, and cytosine. Guanine and cytosine do not have this. They are not two. They have actually 3 hydrogen bonds split between them. That's how you get base pairing. That's one of the ways we proofread our DNA, which we'll talk about in DNA replication. It's all based on hydrogen bonds, right? Because let's say you had a molecule which was OH, and then the same one, ROH. How they're orientated right now, they're both donors. It really wouldn't work. Remember, they're not freely floating like water is. They'd be able to, maneuver themselves. These are tightly packed in DNA. So here, our functional groups are how we have DNA in that double helix. Without this, we would not have our DNA, and we would not be alive. So I hope I was able to show you how it all ties together and impacts us as creatures, right? Not just learning about all these individual things that make absolutely no sense, but now we're tying it together into something, and we're like, oh my gosh, it's it's all coming together. It's making sense. That's my hope with showing you this base pairing, because you're not going to learn about this for quite a few weeks, but now it's in the back of your mind that what you're learning now makes an impact, right? You're going to come back to it. You're not just learning random things. But that is all I have for you today. Good luck with your studies. Good luck in Biz 2A. Good luck with all the rest of your classes. I know you guys are going to do fantastic. Alrighty. Goodbye, everyone.